Greetings! Isang pagbati na puno ng kaalaman. Our topic for today will deal with analytical solutions or exact solutions of partial differential equations. To be exact, first-order partial differential equations. Now, one method that we can use to solve first-order partial differential equations is what we call the method of characteristics. This is lecture number 7. Now, let's first consider this first-order partial differential equation having the following form over here. Okay? Take note that the variables a and b, which are the coefficients of ux and uy, or partial derivatives of any other variable in this case, may be constants or functions of the independent variables. And again, our goal, as with any differential equation, is to find a function u in terms of the independent variables, which in this case, in our equation over here, in terms of x and y. Later on, I will show you that the solution u, which is a function of x and y, is actually a surface generated by a series of curves or lines. Now, in order for us to find the solution of this partial differential equation over here, our first task is to parameterize the equation and obtain what we call characteristic curves. Now, the characteristic curves have the following form as shown in the screen here. Okay? So we can say that dx over dx is equal to a, dy over ds is equal to b, and du over ds is equal to c. Take note that a, b, and c are the coefficients of ux, uy, and the right-hand side of the equation. Now, what we have here, once we have already parameterized, are three equations, which are systems of ordinary differential equations that we can now solve using skills we have learned in solving ODEs. However, the solutions we will obtain from these characteristic curves are just general solutions. To make it a particular solution or an exact solution, what we can do is impose initial conditions to the problem. Now, for us to be able to appreciate and visualize the process of using the method of characteristics, let's try to look at this visual representation. Okay? So, for example, this here is the problem. Given a partial differential equation described initially by what you see in the xy plane, so this is the x and this is the y-axis, at t equals 0. Okay, so at the most front of the xy plane, at the frontmost portion rather of the xy plane, our goal is to find a solution of how this equation propagates through time. Okay? Hence, our goal is to parameterize and look for characteristic curves. Okay? So what are characteristic curves? Your characteristic curves are described by characteristic equations, which are illustrated by curves that you see, curves or lines that you see from the top view. Okay? So if you look at the top view over here, or the xt plane, you will be able to see lines wherein the value of y is constant. Okay? So meaning, in this case, for different values of t, if I look at the top view, my goal is to find what's the equation of this line, of this line, of this line, such that the value of y, if I look at the top view, is constant along this line. Even if x and t varies, at the top view, the value of y does not change. Okay? So this is what you call your characteristic curve or characteristic equations. And finally, the surface made by these characteristic curves is what we call the solution, okay, of the partial differential equation, which we are now interested in. Okay? Now, let's try to solve this example. This is example 7.1 in our lecture slides. We're being asked to solve the partial differential equation with the following condition. Okay? So our problem is 5ux plus 2uy is equal to 0, okay, imposing an initial condition u0y is equal to sine y. So again, just as a visual cue for this problem, okay, so this is the problem we are solving. Let's look at this. This is the yu plane. So y is this horizontal and the u plane, okay, over here is the vertical at t equals 0. Okay, then our goal is, if we look at the top view, okay, if we look at the top view of this box over here, okay, our goal is to find the equation of those lines, okay, wherein, okay, the value of u is constant. Okay? So how do we solve this problem? Okay? So at this point, I now encourage you to grab a copy of this problem while I switch and get my my solving pad. Okay, so this is the problem that we have. 5ux plus 2uy is equal to 0, imposing initial conditions u0y is equal to sine y. So just following our quick discussion earlier, our goal first is to identify A, B, and C from the problem, knowing that the form of the PDE is this one as shown over here. Okay, so again, going back to our previous discussion, earlier, we can say therefore that from our problem, A is the coefficient of ux, so that's 5. Then B is the coefficient of uy, so that's 2. And C is the right-hand side of the equation, which is equivalent to 0. Okay? Our next step is to parameterize and determine the characteristic equations. Now again, what does the characteristic, or what do the set of characteristic equations look like? Okay? They should have the following form, as we have mentioned in our earlier discussion. Dx over ds is equal to A, dy over ds equals B, and du over ds is equivalent to C. Okay? And furthermore, I can say that these three sets of equations would actually be equal to this one. I can say that once I cross multiply, I can say that dx over A is equal to ds, dy over B is equal to ds, and du over ds, or du over C rather, is equal to ds. Is that clear? Therefore, if everything, all of these three equations are, all these three terms are equal to ds, we can say that dx over A is equal to dy over B, which is also equal to du over C. Are we clear? Okay. Therefore, what I do now is to write dx and just follow the form. Dx all over A, so that's dx over 5, is equal to dy over 2, is equal to du all over C, which is 0. Okay? So these are now the set of characteristic equations that will form our characteristic curves. The next step here is, from this solved equation, or from this written equation from the previous step, my goal is to now solve this system of ordinary differential equations produced by the characteristic equations by selecting 2 out of the 3 available equations. Why do we have 3 available equations from this one? Okay? So we actually have 3 available equilibrium equation. 3 available set or system of equations, okay, such that I can say that dx over 5 is equal to dy over 2. I can also say that dx over 5 is equal to du all over u. And I can also say that dy over 2 is equal to du over 0. So my task is to select 2 out of the 3 available equations in order to solve my problem. But how do I do that? Right? So what I will do is, or which of these 3 do I select? Right? So the first equation that you select is, pick the equation, right, wherein du is absent, right, or wherein you cannot see, right, the derivative or the partial derivative of u. Right? So in this case, that equation is this one over here. Right? So we don't see any du. Next, how about the second equation? Our second equation is, you go back, right, to the initial condition. Okay? Now, if we look at the initial condition, we can say that the initial condition is that, right, we are given the value of u at x equals 0, correct? So this is x over here, right? So meaning, whichever is set as 0 right, in your initial condition, right, yun yung hahanapan ko ng partner ng du. So in this case, du partnered with, right, differentiation or the partial derivative of the variable which is 0, so x. Right? So I'll now find an equation that is where du is partnered with dx, right? Because x is set as 0 in the initial condition. So this is the second equation. Du is partnered with the variable that is initially set as 0. Okay? So that's dx. So we now have 2 equations, and as you can notice, these 2 equations are just ordinary differential equations which are actually separable even. Okay? Therefore, our task now is to solve. Okay? So to solve, our first equation, dx over 5, is just equivalent to dy over 2. I can say here that dy is just equal to 2/5 dx, correct? Or the other way around, it's okay. Dx is equal to 5/2 dy. It's not a problem. At the end of the day, bottom line is you'll get the same answer. Then I will integrate. Okay? Once I integrate over here, I should have y is equal to 2/5 x plus a constant of integration. Now, you might ask, sir, where do I write the constant of integration? Why have you written it at the right-hand side of the equation where x is found and not on the left-hand side? Anywhere will do, right? You'll get a different answer, but at the end of the day, when you continue solving, okay, you'll get the same form, you'll get the same answer. You should get the same answer, okay? So let me call this equation and let me label this as equation number 1. Our next task, as with any differential equation, is to solve for this constant of integration by imposing our initial condition. Knowing that our initial condition is u, 0y is equal to sine y, meaning at x equals 0, for any value of y, okay, the value of u is sine y. Okay? Now, what I'll do is I'll take another variable so as not to confuse you. I will rewrite the initial condition as u of 0 epsilon, meaning I am taking any arbitrary point, right, at y, equals sine epsilon. Okay? So epsilon is any point, okay, along y. Now, this is the initial condition such that we can say that, please remember, 0 over here is x variable, epsilon here is the y variable, and sine epsilon here is the u, okay, is u. Okay? Therefore, these are now the initial conditions, okay, such that from equation number 1, okay, I'll impose the initial conditions from equation number 1 over here, y, which is, again, from our initial condition, y is just epsilon, correct? Okay, so this is epsilon, okay, equal to 2/5 times x, but x in our initial condition is 0, plus C1. Therefore, C1 is equivalent to epsilon. Okay? Therefore, I can rewrite equation 1 as, I can now cancel C1 and change that to y is equal to 2/5 x plus epsilon. So this is now my solved equation, my solved ordinary differential equation, and let me call this equation A. Is that clear? I hope it is. Our next equation, okay, from the selection over here is dx over 5 is equal to du over 0. Okay? So again, this is just a simple ODE such that what I can do is, this is just, okay, du is equal to 0, correct? So I can cross multiply. I place 0 on the upper left-hand side. Okay, so du is equal to 0. And once I integrate, okay, once I integrate this one, I would be able to say that u is just equivalent to some other constant. Correct? Okay, so if I integrate 0, I know that that will come from a constant number. Okay, so let me call this equation number 2. Okay, now again, as what we have done, our goal is to solve for the constant of integration C2 by imposing the initial condition. So going back, our initial condition is u 0y is equal to sine y. And remember, I can rewrite this as u 0. Then I'll just take, to avoid confusion, para hindi pa ulit-ulit yung ating variables, okay, u 0 epsilon is just equal to sine epsilon, meaning I am taking any epsilon, any value, okay, in the y plane, y axis. Okay, let's say that point is epsilon, and the value of u, okay, 0 epsilon, or the initial condition, is sine epsilon. Okay, such that 0 here is x, epsilon here is y, and again, sine epsilon here is the value of u. Okay? So going back to equation 2 over here, okay? So going back to equation number 2, so from equation number 2, what we can conclude here is that u is equal to C2. So imposing our initial condition, we said here that u is just equal to sine epsilon, correct? Okay? So that's just sine epsilon. I'm just copying equation 2 but imposing my initial conditions, equals C2. Okay? So that's actually the value of my constant of integration. Therefore, okay, I can now rewrite equation 2 as u is equal to C2, which we have found to be sine epsilon. Okay? This is now what we call, or what I should label as, equation B. Okay? Are there any questions? Okay? And finally, our task is to obtain the solution u. Okay? But in terms of the two independent variables, which are in our case, x and y, by eliminating epsilon. Okay? Such that I know that equation A over here is y equals 2/5 x plus epsilon, and b is equal to u equals sine epsilon. So I just called equations A and B. So my goal is to find u in terms of x and y. So I cannot have equation B as my final answer because there's epsilon. Therefore, I can say from equation A here that epsilon is equivalent to y minus 2/5 x. Therefore, if I plug in equation A, which is already in terms of y and x, okay, I plug it into equation B, okay, my final answer would be u, which is now a function of x and y, is equal to sine, instead of epsilon, I know that epsilon is y minus 2/5 x. Okay? So that is the solution to problem or example 7.1. At this point, are there any questions? I hope you were able to absorb, okay, the solution for example 7.1. Okay? Okay, let's proceed. Our next example is example 7.3. Okay? So example 7.3, so I already obtained here a copy of the example for you. Example 7.3 is ux plus 2x uy is equal to 2xu, given an initial condition ux0 is equal to x squared. Okay? So again, our first step is to identify A, B, and C, given that this is the form of our partial differential, our first order. Let me remind everyone that the method of characteristics is used to solve first order PDEs. Okay? So I can say now from the given problem that A is just the coefficient of ux, that's 1. B is the coefficient of uy, so that's 2x. And C is the right-hand side of the equation, which is 2xu. Okay? Our next step is to parameterize and determine the characteristic equations. Remember, having the form from our previous slides, dx over ds equals A, dy over ds equals B, and du over ds equals C. Or that's also similar, as I have explained earlier, to this set of equations over here once I rearrange the variables. Okay? Therefore, following this boxed set of equations, I can now write dx over A, which is 1, equals dy over B, which is 2x, equals du over C, which is 2xu. Okay? Is that clear? After that, okay, my next goal is again to select 2 out of the 3 available equations. Okay? From my characteristic equations, I can say that the 3 equations are dx over 1 equals dy over 2x, dx over 1 equals du all over 2xu, and dy over 2x equals du all over 2xu. Now again, what's the first equation that we select? We select the equation wherein du is absent, or we won't see any du, right? And that is this equation over here. Correct? Next, how do we select the second equation? Okay? I select an equation wherein du is partnered with the variable which is 0 in the initial condition. So going back to my initial condition, this is ux0, therefore this is x and this is y. Okay? Such that, again, y variable is set to 0, therefore, okay, so y variable is set to 0, therefore I'll pick du partnered with dy. Okay? Is that clear? So du partnered with dy is this third equation over here. Okay? So I only need those 2 equations in order for me to solve the problem. Okay? So let's now have the first equation, dx over 1 is equal to dy over 2x. Again, this is just an ODE. Okay? Therefore, I can separate and say that this is, okay, let me solve over here. This is 2x dx is equal to dy. Okay? Correct? Then I integrate such that I would be left with x squared is equal to y plus c1. Again, you can place the constant of integration anywhere. That's not an issue. Then this is what we call equation number 1. And our next task, as always, is to solve for the constant of integration. How? By imposing our initial condition. Okay? So our initial condition is ux0 is equal to x squared. Okay? Therefore, let me just copy again, but change the variables to avoid confusion. U epsilon 0 is equal to, I'm changing x to epsilon. And please take note that epsilon here is x, 0 here is y, and epsilon squared here is the value of u. Okay? So these are now the initial conditions for a certain point, okay, anywhere along x, such that I can now impose my initial condition from equation number 1, okay, imposing my initial conditions, okay, x squared, so x is just epsilon, so epsilon squared is equal to y, which is 0 from my initial condition, plus c1, okay, that tells me that c1 is equal to epsilon squared. Therefore, I can again rewrite equation 1, okay, having solved the constant of integration as x squared is equal to y plus constant of integration epsilon squared. This is now what we call equation A. Are we clear? Okay. Next, my next task is to use the next equation, dy over 2x is equal to du all over 2xu. Okay? So what I'll do here is, this is actually separable once I cross multiply or I transfer 2xu to the left-hand side of the equation, 2x cancels out, correct? Okay? And I can say that I am actually left with du over u is equal to dy. Agree? Okay? Then I integrate. Okay? I know that if I integrate this left-hand side, I am left with L and U. And on the right-hand side, this is y plus another constant of integration, C2. Again, you place it anywhere, you should arrive at the same answer. Okay? No problem at all. Same final answer, rather. Okay? Now, I can rewrite this. You should agree with me when I say, okay, reviewing your math skills, okay, we can also write this equation as u is equal to e raised to y plus c2. Correct? Okay? And please remember that e raised to y plus c2 is also known as, is actually a property, multiplication property, e raised to y times e raised to c2. Agree? And I know that e raised to c2 over here is actually a constant. Okay? Therefore, I can just say that I'll absorb that constant. U is equivalent to another constant, b, e raised to y. Okay? So this is now, okay, let me call this equation number 2. Okay? And next step is, again, let's just solve for the constant of integration b by imposing our initial conditions. Ux0 is equal to x squared. Okay? Again, I know that I can write, okay, u epsilon 0 is equivalent to epsilon squared. Just as a reminder, okay, people, epsilon is x, 0 is y, and epsilon squared here is u. Okay? So these are now our initial conditions. Okay? Therefore, okay, from equation number 2, I should now be able to solve equation number 2. Okay? U is equal to b e raised to y. So u is just equivalent to, we said, that's epsilon squared. That's the initial condition. Okay? Is equal to b, that's an unknown which we are solving, e raised to y, so e raised to 0. So e raised to 0 is 1. Therefore, okay, b is just equal to epsilon squared. Therefore, I can again rewrite equation 2, okay, as u is equal to b. I already know b, which is epsilon squared e raised to y. This is now my equation b. Okay? So lastly, now that I know equation A and B, okay, so my goal is again to solve u in terms of the two independent variables, which in this case is x and y, by eliminating epsilon. Okay? So I now have equation A and equation B. Okay? Looking here at equation B, this should be our final answer, but it has epsilon. So I can cancel epsilon by rearranging equation A over here and saying that, okay, epsilon squared is just equal to, rearranging equation A, x squared minus y. Okay? Therefore, my next task is to place equation A in terms of x and y into equation B, okay, such that my final answer now is u as a function of x and y is equal to epsilon squared, which I already know is x squared minus y, e raised to y. This is now our final answer. Okay? At this point, are there any questions? I hope you were able to understand, okay, solving problems using the method of characteristics. Now, just to go back to our set of slides, this is example 7.1. Right? Given that final answer, kindly double check if the final answers that we obtained in solving is the same as the one shown here. And our second example is this one. Right? And we have already solved example 7.3. Right? So this is example 7.3. And kindly double check that the answer shown in your screen is the same as the one I solved earlier. Okay? So as an application of what we should have learned today, kindly solve example 7.2, okay, given a partial differential equation here. Example 7.2 is actually similar to example 7.1. Okay? So the final answer here is given as well. And finally, you can also solve example 7.4. Example 7.4 is now similar to example 7.3, which we have solved earlier. The final answer is also given here. Okay? So that ends our short lecture on method of characteristics, which is again a method used to solve first-order partial differential equations. If you have any questions or you wish to consult, don't hesitate to send me a private message or send me an email. Okay? Till our next lecture, thank you very much.